Hello everyone, in this lesson I will continue to explain the first chapter, Application of Crystal Diode. Using the unidirectional conductivity and reverse breakdown characteristics of a diode can constitute a rectifier circuit, a voltage regulator circuit, and a limiter circuit, and so on, a variety of functional circuits. In this lesson, we will focus on the following three aspects of its application. First, let's look at rectifying and voltage stabilizing circuits. Rectifying and voltage stabilizing circuits are in the power supply equipment. It is essential to make a circuit. The main function of the power supply is to convert the AC voltage provided by the power grid to 220 volts, the frequency to 50 Hz, such as AC voltage, into a stable DC voltage for output. So in the process, it needs several functional circuits. First, the AC voltage provided by the power grid, 220 volts, 50 Hz signal. Let's call it V. V is a sinusoidal voltage. After the power transformer, V is changed to a suitable AC signal voltage VI. Then, VI will continue to be sent to the rectifier circuit. Because VI is also an AC signal, we want to turn it into a unipolar voltage signal. The rectifier circuit realizes the conversion of the AC signal into a unipolar voltage signal. At this time, V1 is already a unipolar voltage signal, but it is still a changing signal. Then we send this VI to the filter circuit. After the filter circuit, it finds the average value in V1. Filter out the signal, it fluctuates, so when V2 comes out, it is basically a slightly changed ripple signal. V2 needs to be further stabilized because its voltage still fluctuates slightly. So we send V2 to the voltage stabilizing circuit. And finally, the output of the voltage stabilizing circuit, the signal VO, is a constant DC voltage. This is a power circuit. There is usually such an internal structure and the conversion function of the signal. Then let's take a look at the rectifier circuit, its composition and functions. The circuit diagram on the right is the rectifier circuit. It is composed of diodes. This is the simplest rectifier circuit. Transformer will test 220 volts and 50 Hz, converted to the voltage of the negative terminal of the transformer VI. Then, VI in the rectifier circuit is an input AC signal. In this circuit, diode is conduction voltage drop VD on relative to the input VI is very small, so it can be ignored. Then, this diode can be regarded as an ideal diode, but it is used as a switch. We can understand this as when VI is greater than 0, diode conduction. Then the voltage drop VO across the resistor R is equal to the input signal VI. So VO is also a positive half-cycle waveform, sine wave of positive half-cycle. But when the negative half of VI is less than 0, the diode is cut off. The diode cut-off switch is off. VO is 0. VO equal to 0 means that when VI is in the negative half of the weak, it has no output voltage. So we can draw the waveform of VI and the waveform of VO separately. So we can see that the rectifier circuit realizes an AC signal such as VI, transformed into a unipolar voltage VO signal. This is half-wave rectification. Of course, this is the simplest. Then the diode can also form a full-wave rectifier, etc. You can check some information to see. Next, we will introduce the voltage regulator circuit, AC signal converted to unipolar signal. It also needs to be filtered to remove part of its fluctuations and take the average, but this filtered signal voltage will still fluctuate slightly. Therefore, it needs to be sent to a voltage stabilizing. The so-called voltage regulator circuit is when the input voltage, load, ambient temperature, and circuit parameters change. It can keep the output voltage stable all the time. Such a circuit, the voltage regulator circuit we are going to talk about, is mainly composed of a voltage regulator tube. Its circuit symbol is usually such a symbol, which is different from the diode. Is that there is a slight difference in the symbol, is such a shape. Regulators usually work in breakdown state. When the diode is breakdown, Let's look at the volt-ampere characteristic curve on the right. This part is the volt-ampere characteristic of the diode or Zener tube in the breakdown state. When the diode breaks down, the voltage Vz remains almost unchanged because its limit is very steep. Working current Iz of voltage regulator, the current Iz should be between Iz minus and Iz max. In other words, it has an upper limit working current and a lower limit working current. The lower limit working current ensures that it is stable at the breakdown state. The upper limit of this current is to limit it from being burned. This is the scope of Iz's working. If you analyze the voltage regulator in the circuit, if it is in the DC state, the large signal model uses such a model. It is described by a stable voltage Vz. If it is analyzed for small signals, it is also equivalent to resistor Rz. Let's take a look at the voltage regulator circuit. This figure is a voltage regulator circuit composed of a voltage regulator tube. Input voltage Vi. The voltage at the output is Vo. Here we look at Vo. It is equal to the voltage Vz at both ends of the voltage regulator tube. The input voltage is equivalent to the stable voltage of the voltage regulator tube. So Vo is equal to Vz. In this loop, there is also a resistor R, which is called current limiter resistance. The current limiting resistor means that it should limit the current in the loop to ensure that the voltage regulator works between Iz minus and Iz max, and ensure that the current can make the voltage regulator work normally. Its principle of voltage regulation. Let's take a look. If for some reason the voltage Vo of the output terminal increases, in this case, according to the volt-ampere characteristics of the volt regulator, its current Iz will also increase. If Iz increases, the total current I in the loop will also increase. If I increases, the voltage across the current limiting resistor R and the voltage drop V on R will also increase. If this voltage is increased, the increased trend of Vo will be surprised. The trend of increasing Vo is surprised. It will make it tend to stabilize, so it can maintain a stable voltage, which is a voltage regulator circuit composed of voltage regulators. Let's look at the limiter circuit again. Limiting circuit is also called clipping circuit, which is also to limit the voltage range of the input signal. Limiting circuit is divided into bidirectional limiting circuit and a unidirectional limiting circuit. The so-called bidirectional limiting circuit is a limiter circuit with two upper and lower thresholds. Unidirectional limiting circuit is a limiting circuit with a threshold. We analyze from two-way limiting characteristics and one-way limiting characteristics. First, look at the two-way limiting characteristic. In this picture, we look at the graph on the left. The abscissa is Vi and the ordinate is Vo. The so-called Vi is the input signal of the limiter circuit. Vo is the output signal of the limiter circuit. Vi has two thresholds. One is VIH. This is VIL. VIL is called the lower threshold. VIH is called the upper threshold. When the voltage of Vi is between VIL and VIH, when the voltage is within this range, let's take a look at the transmission characteristics of input and output. This curve is a straight line segment. A straight line indicates that Vi and Vo are linearly proportional. Vo changes as Vi changes. But when Vi is greater than VIH, the Vo at this time is equal to Vo max, also known as the upper threshold voltage, which means that Vo no longer changes with the change of Vi. It is limited to a certain potential. At this time, it is limited to Vo max. When Vi is less than VIL, let's take a look at this transmission characteristic. At this time, Vo will not change anymore. It is Vo minus. In other words, if Vi is less than the lower threshold, the output voltage Vo no longer changes with Vi. It is limited to the voltage of Vo minus, so we call it two-way limiting. It is equivalent to that if the waveform exceeds these two thresholds, the voltage at the output will be limited to a certain potential. We assume this voltage Vi at the input is such a waveform, a sinusoidal signal. In the process of a sinusoidal signal changing, at some point, its voltage will exceed VIL, and it will also exceed VIH, lower than VIL. the voltage above the threshold will be flattened. Therefore, the voltage VO at this output should be such an output signal. The upper and lower peaks are flattened. Such an output voltage is a bidirectional limiting characteristic. Let's look at the unidirectional limiting characteristic. This is the upper threshold, with the limiting voltage characteristic of the upper threshold. Let's look at the VI input signal. If it is less than VIH, VO changes with VI to a limited proportional relationship. But when VI is greater than VIH, VO no longer changes with VI, and its voltage is limited to VO max. VIH is called upper threshold. This is the upper threshold limiter circuit. Looking at the lower threshold again, when VI is greater than VIL, VO and VI are in a proportional relationship. VO varies with VI. But when VI is less than VIL, VO is limited to the voltage of VO minus and no longer changes. This is called the lower threshold limiter circuit. Let's take a look at an example. Bidirectional limiting circuit composed of diodes. The picture on the left is composed of diodes D1 and D2, composed of two-way limiting circuits. Among them, the two voltages of V1 and V2 are used to control its threshold voltage value. This is V1. This is V2, used to control the upper and lower thresholds in the limiting circuit. Then, for this diode, we can use its constant pressure drop model to describe. You can ignore its resistance RD. Its constant voltage drop means that the diode is equivalent to a DC voltage source VD on. D2 is also VD on 2. The turn-on voltage of D1 is called VD on 1. In this circuit, its upper and lower threshold voltage value, we can look at it this way. VIH is equal to VI plus VD on 1. In this branch of the circuit, D1 diode and V1 power supply is series. If the diode can conduct, the voltage value at this point is greater than VD on 1. Adding a voltage sum like V1 can make this branch conductive. Then, look at this branch. Its voltage is positive below and negative above. If you want to make this branch conductive, the voltage value at this point should be less than the negative V2 plus VD on 2 plus the sum of these two series voltages. Let's analyze. The input signal in this circuit is VI. The output signal is VO. If these two branches are not connected, what should the VI be? Does not turn on. That is, VI is less than VIH and greater than VIL. Let me talk about it in detail. That is, the VI is smaller than the left branch. Its turn-on voltage larger than this branch on the right. At this time, these two branches are not connected. If they are not conducting, no current flows. VO and VI are equal. Therefore, if VI is less than VIH and greater than VIL, both D1 and D2 tubes are closed. At this time, the output voltage changes with the change of VI. Another situation, if VI is greater than or equal to VIH, the signal at the input is greater than or equal to the conduction voltage of this branch. At this time, the branch is open. At this time, the second branch is still non-conducting. After the D1 diode branch is turned on. At this time, VO is connected to the power supply V1 through the diode D1. The output voltage of VO has nothing to do with VI. What is the voltage of VO at this time? Is equal to VD1 on plus V1, the value of this DC voltage. So it means that it's equal to VIH. In this case, VO is equal to its highest threshold, which is VIH. Let's look at it next. If VI is less than or equal to VIL, the branch where D1 is located is non-conductive, because the voltage is very small and it is negative. It is absolutely non-conductive. After it is less than the lower threshold, the D2 path is conductive. After it is turned on, the voltage value of VO has nothing to do with VI. Its voltage value is equal to V2 plus the diode D2 turn-on voltage. That is, VIL is a negative value. So VO equals VO minus equal VIL. So we can see that the limiter circuit composed of these two diodes. After VI is limited, the voltage at the input is such a waveform. That is, the part that exceeds the upper and lower thresholds is flattened, such as sine wave. This is a function of the limiter circuit. Okay, about the application of diodes. Let's talk about here first. Thank you all. The content of this lesson is here. Thank you.